G'day McGrathletes, welcome back to a brand new episode of Maths for the Extension 1 HSC course. Today's lesson is going to be covering a variety of trigonometric integration that we cover in Extension 1. Before we do that, we're starting off with a flashback to integration by substitution. This is an HSC question from 2013. Multiple choice, it's asking us which of these integrals do we obtain when we apply the substitution u equals 1 plus 2x to the integral of x times the square root of 1 plus 2x dx. Okay, so with our integration by substitution questions, we run through the checklist. First thing is to change our limits. This question has no limits, that's already done, which is great. Now we go ahead and change the dx. So we take our substitution, which is u equals 1 plus 2x, and we say the derivative of u with respect to x, differentiating the right hand side turns into 2. Okay, now we want to rearrange this to make dx a subject so we can sub it into our integral. So we're just going to multiply the dx across and divide the 2 underneath to get du on 2 equals dx. Now we can sub that into the integral. So putting it in, the dx turns into a du over 2. Inside the square root, we have our substitution, 1 plus 2x equals u. Now that we've subbed everything in, we can see we still have an x here that it's not going to cancel out with anything. So we've got to fix that up. So when there's still x's in your integral, you go back to your substitution and figure out how can I fix that. So we're going to rearrange our substitution to make x the subject so we can sub it into here. So u is equal to 1 plus 2x, so we'll minus the 1 across to make u minus 1. Now we can divide both sides by 2 and say that x is equal to u minus 1 divided by 2. Putting that up in here looks like this. Now the over 2 and the over 2 are going to turn into an over 4 that we can put out the front, and we'll have u minus 1 multiplied by the square root of u, which looks like that, and that's where we can stop because that looks exactly like option A, 1/4 integral u minus 1 square root u du. So this substitution turns into the first integral, and we could then go ahead and integrate that by expanding and doing all the usual nonsense. But for today, option A, gets us 1 mark in 2013. Okay, now onto the lesson. So like I said, we're running through a bunch of different trig expressions we can be expected to integrate in the Extension 1 course, mainly focusing on how we integrate sine squared and cos squared because they're very useful. All right, so our first task for today is we need to figure out a way of integrating cos squared. And no, we can't just raise the power and divide by 3. It doesn't work like that. So a lot of the integrals today will rely on us being pretty familiar with a fair few trigonometric identities. Some of these are on the reference sheet, some of them are not. First one is that cos 2x is equal to 2 cos squared x minus 1. I don't have time to run through the full explanation of where we get this from, but that's covered in the year 11 course. Okay, rearranging this by putting the plus 1 across here with the cos 2x and then dividing both sides by 2, we end up with cos squared equal to a half plus a half cos 2x. We factor the half out, and this right here is our substitution for cos squared. Okay, the right hand side is much easier to integrate than the left hand side. And that's where we get this expression from, which is on the reference sheet. It's a more generic one for cos squared something x. A half times 1 plus cos 2 times the something x. So whatever this angle is here, you double it here with your cos. Okay? So changing our cos squared x to be this for our integral, we can just put the half out the front to make our lives a little bit easier. And now we go ahead and integrate. 1 turns into x, cos integrates to sine, and we need to also divide by the derivative of the angle, which is 2. So 1 turning into x, cos turning into sine, angle remaining the same, and then dividing by 2, which is why there's a half there. Don't forget your plus c, and now we can expand it out and get a half x plus a quarter sine 2x plus c. And that right there is the integral of cos squared x. So lucky thing is we don't have to memorize any of this because the thing in the green box, like I said, is on the reference sheet, but you've got to recognize when you're integrating cos squared or sine squared, you need to reach for the reference sheet if you haven't remembered this. Another quick example of how we do a similar approach for sine squared. We start off with our identity cos 2x equals 1 minus 2 sine squared, and we rearrange this to make sine squared the subject. So we're going to put the 2 sine squared across to the left to make it positive. We'll put the cos 2x across to the right to make it negative, and then divide both sides by 2, and we get a half minus a half cos 2x. Okay, factor out the half, and it looks like this, and that's where we get this expression from on the reference sheet. This is a substitution for sine squared turning it into a more calculus-friendly version, much easier to integrate. So going back to our question, writing sine squared x as a half of 1 minus cos 2x, and now the integration is very similar. 1 turning into x, cos turning into sine, dividing by a half, it's still negative, and the angle is still 2x, and there's still a plus c. So very similar result from the formula sheet. Okay, that's the backstory. Now let's go into a variety of questions and then finish off with a couple of HSC questions to show you the kind of stuff that you can be expected to do in the HSC and in any upcoming assessments. Pardon me. Cool little starter. Okay, example 1, cos squared 3x minus 3x squared dx. Okay, so we see integral and we see cos squared. So we reach for the formula sheet and we just make sure we have this ready to go. So cos squared 3x is going to be written as a half of 1 plus cos 2 times 3, so 6x. So again, whatever your angle is with cos squared or sine squared, the substitution is going to double that angle. That's why there's a 2 there. So we're going to split this up into two integrals. The minus 3x squared we're going to do on the end to make our lives a little bit easier. Cos squared 3x we've written as a half 1 plus cos 6x, and now we're ready to go ahead and do some integrating. Keep the half out the front. 1 turns into x, cos integrates to sine, dividing by 6 because 6 is the derivative of the angle. So that's that part done. The 3x squared, we're raising the power to become a 3. We're dividing by the new power of 3 and then adding our plus c. Now we're just going to simplify. We can expand out the brackets by timesing everything by a half, and of course a 3 over 3 we can just write as 1x cubed. So making it look a little bit nicer, it looks like this, x over 2 and then sine 6x over 12. Don't forget your plus c, or you owe me 10 push-ups as always. Okay, example 2, similar idea. We got some trigonometry, and as soon as we see integration and we see a sine squared, we've got to go to the reference sheet in case we've forgotten this, because this is our substitution for sine squared to make it more integration friendly. Okay, so splitting it up again, we'll just do the sine 2x at the front. Okay, still got our limits on both integrals. The sine squared has turned into a 1 minus cos 2x with a half out the front. Now we can go ahead and do some calculus. So sine 2x, once again, sine is going to integrate to negative cos. So this will turn into minus cos 2x divided by 2, as we can see here, okay? Minus cos 2x divided by 2. Negative a half out the front of the second integral. 1 is integrating to x, and then cos 2x is integrating to sine 2x divided by 2, okay? Now we can put in some limits. All right, it's going to get a bit hectic here, but here we can see us putting in, if you want to make your life a little bit easier, for this first integral, you can take the negative out the front, as I've done here, but that's completely optional. Subbing in pi on 6, 2 times pi on 6 is going to be equal to, well, it's kind of like you're doing 2 times 30. It turns into 60, which is pi on 3. So we have cos pi on 3 over 2, take away cos 0 over 2, and be careful because cos 0 is not equal to 0, it's equal to 1. Negative a half at the front of the second expression, subbing in pi on 6 here for x, and then once again, pi on 6 is 30 degrees. When we double it in the angle, it turns into 60, which is pi on 3, and we've still got the divided by 2 here. Okay, now we need to evaluate a bunch of stuff. So we have cos pi on 3, well that's cos 60, which is a half. So when we do a half divided by 2, it turns into a quarter. Cos 0 is equal to 1, which you can verify with your calculator or just by knowing what the graph of cos x looks like. So this turns into 1 over 2. Negative a half out the front, pi on 6 still here, and then sine 60 or sine pi on 3 is root 3 on 2. So when we divide that by 2, it turns into root 3 on 4. So that's all the calculus done. That's all the subbing in done. Now we're just going to try and simplify this as best we can. So our first fraction is going to turn into a quarter minus a half, which is a negative a quarter. But there's a negative out the front, which makes it a positive quarter. We have a negative a half times pi on 6, which is negative pi on 12. And then when we times negative a half to this, two negatives make a positive. We get 1 times root 3 is root 3. 2 times 4 is 8. Okay, we can join it all together as one fraction if we make all the bases equal to 24, but this last step is optional. I'd say this answer right here would be getting you full marks for a question like this. But there it is, all simplified as one fraction if you want your best possible answer as one succinct, simplified term. So well done if you got that far, but that third last line right there is probably going to be 4 marks. Okay, on to example 3. We have sine squared cos squared. So we know how to integrate sine squared. We know how to integrate cos squared. When they're timesing together, things get a little bit trickier here. So to efficiently handle this integral, we're going to use the fact that we know that sine 2x is equal to 2 sine x cos x. Okay, once again, don't have time to fully explain this, but this is covered in the prelim course. So if you need more help with that, let me know in the comments and I'll give you some guidance. All right, so if sine 2x is 2 sine x cos x, if we divide both sides by 2, we get that sine x cos x is equal to a half sine 2x. Now, in the question we're looking at, we don't want sine x cos x, we want sine squared cos squared. So taking this second line in blue and squaring both sides, we get a half squared is a quarter, sine becomes squared, and on the right hand side, sine and cos both get squared as well. So this right here is our substitution that we're going to make for sine squared cos squared into our integral. So instead of integrating this on the right, we're going to integrate this on the left because it's one term, so it's a bit easier to handle. Okay, so now we are integrating just sine squared. So once again, trusty formula, sine squared x equal to a half of 1 minus cos 2 times the angle x. So this in green inside our integral is going to turn into a half of 1 minus cos 4x because the angle is always being doubled. So we have a half 1 minus cos 4x dx. We can take that half out the front with the quarter and turn it into an eighth because a quarter times a half is 1 over 8. Okay, now we can integrate. So 1 is going to integrate to x as always, and cos integrating to sine with the dividing by 4 because that's the derivative of our angle. So same stuff over and over again. Okay, 1 going to x, cos going to sine, dividing by 4. Don't forget your plus c as always, and now just expand out by multiplying everything by an eighth, and we get x over 8 minus sine 4x over 32 plus c as our final answer. So quite a bit of work to do there, and it all relied on us recognizing that sine squared and cos squared can be manipulated with this identity here, which is not on the reference sheet. It's got to be a part of your content knowledge to obtain this substitution here to then move forward. So yeah, a pretty tough question if you're not really sure where to start, which is how most of these questions typically play out. Knowing where to start is like half the battle, honestly. Okay, on to example 4, which is pretty similar to the other ones, so we'll go pretty quick. We have 1 minus cos 4x squared. If you're not really sure where to go from here, it never hurts to expand and just see where you're going from there. So expanding out our perfect square, we're going to do 1 squared is 1. For the middle term, we're going to multiply both things inside our bracket to get negative cos 4x and then double it. So this is like a squared minus 2ab plus b squared. And then cos squared is right there, of course. Okay, now we know how to integrate 1. We know how to integrate cos 4x. To integrate cos squared 4x, we're once again reaching for that useful identity on the formula sheet, which looks like this. So cos squared 4x is going to be equal to a half times 1 plus cos 8x, doubling the angle once again, same stuff every time. So writing it like that, we can write cos squared 4x as a half plus cos 8x over 2. That's just me expanding out the half into the bracketed term here. This is just so I can go through and do it all in one integral. You don't have to do it like this. If you want to split it into 2 and do this one first and then do this one second, that will work as well, but it's optional. So it's depending on your preference. If you want to tackle it all at once like this, go for it. Okay, time for a bunch of calculus. So here we have 1 integrating to x, cos integrating to sine, and then dividing by 4 because that's the derivative of the angle. Same stuff, yada, yada, yada. A half integrating to x over 2, or a half x, and then cos once again integrating to sine, angle staying the same, and that 2 is going to get multiplied by the 8 because we are dividing by the derivative, which is 8. And so the 2 turns into 16. Okay, now it looks like a bit of a mess, but thankfully, sine of 0 is equal to 0. So when we sub 0 into 1, 2, 3, 4 terms, they're all just going to turn into 0. So the second half of the substitution is going to be really friendly. All we have to worry about is the pi on 4. So let's think about that. If x is pi on 4, 4 lots of pi on 4 will be equal to 4 over 4, which is 1. So this will just turn into sine pi. And 8 lots of pi on 4, or 8 quarters, is equal to 2. So this will turn into sine 2 pi. So subbing in pi on 4, we get the x turns into pi on 4. The sine turns into pi. This turns into, so x is pi on 4, so half of pi on 4 is pi on 8. And then, like I said, 8 times pi on 4 is 2 pi, so we have sine 2 pi here. And then I'm just writing minus 0 on the end, just to show that when I sub 0 into all 4 terms, they all just turn into nothing. Okay, now thankfully, if you check with your calculator or you remember what sine looks like, sine at 180 is equal to 0, and sine at 360 is also equal to 0. So this second term and this fourth term are just going to turn into zeros, and we're just going to end up with pi on 4 plus pi on 8. So 0 there, 0 there, 0 on the end. The only thing remaining is a quarter of pi plus an eighth of pi, so we end up with 3/8 of pi as our final answer for this entire integral. So starts off really messy, but simplifies really nice if you just are very careful and just remember your values of sine. Okay, and up next is example 5. Looks very scary, but once again, if you know where to start, it's actually very straightforward. We have 2 times sine 4x cos x. Now, whenever you have sine and cos multiplying and the angles are different, you just want to go to your reference sheet and look up your products to sums formulas. If you're not sure what I'm talking about, here's one of them. This is sine of an angle times cos of an angle. Reference sheet says it's equal to a half times sine of the angles plus and then plus sine of the angles subtracted. So we can use this to turn a product, which is very difficult to integrate, into a sum, which is very easy to integrate. In this scenario, A is going to represent 4x and B is going to represent x. So our sine, our first one's going to turn into 4x plus x, which is 5x. And our second one is going to turn into 4x minus x, which is 3x. So writing that in, I'm just going to put the 2 at the front for now, and then rewriting sine 4x cos x using this identity as a half of sine with the angles plus sine of the angles minus. Hopefully that's making sense. Fortunately, the times 2 and the half just make a 1, so it's kind of like they're cancelling out. So we can just forget these and we can just do some integration. Don't forget that sine integrates to minus cos. This one we're dividing by 5 because that's the derivative of the angle. This one we're dividing by 3 for the derivative. And yeah, both of them turning into negative as sine does when you integrate it. And then don't forget the plus c on the end, and then you're done. So this can be a question that you can achieve in 2 or 3 lines of working if, like I said, you just recognize the starting point, which quite often is just finding the most useful bit of information on your reference sheet. Okay, and then example 6 is another different type of question that we can see. And again, it's all about where to start and finding the right formula. Now, to very quickly handle this integral, all you need to recognize is that we have a sine to the power of 4, and the derivative of sine is equal to cos, as we've explored before in the advanced course. So this question is actually really primed for us to use our reverse chain rule from the reference sheet, which says that when you're doing the integral of a function to a power, and that function is being multiplied by its derivative, we can just kind of let this derivative vanish and just integrate the function. So the answer is the function being raised to a new power, dividing by the new power, and then plus c. Okay, because we'd normally be dividing by the derivative, but it gets cancelled by the derivative in the question, and it all works out really nicely. Okay, so we're just applying this property here. Our f of x is equal to sine. Our power is 4, so we're just going to keep the function there, keep it as sine. We're going to raise the power to 5. We're going to divide by the new power of 5. And the cos x is just magically vanished. Poof, done. Plus c. If you're not sure where I'm getting this green formula from, it is in my integration guide for the advanced course where I look at harder applications of the chain rule. But yeah, this is a formula that's tough to get comfortable with, but really useful for extension 1 and especially extension 2 students. So applying this, like I said, the sine is turning into a power of 5. We're dividing by the new power of 5. The cos is vanishing, and then just don't forget your plus c, and then bingo, done. Okay, so just knowing the correct starting point, being familiar with your reference sheet and how to use it properly can make a lot of extension 1 integrals much easier. Okay, let's finish off with a couple of HSC questions. If you are following today and you want to pause and try these by yourself, by all means, that's how you get the best value out of these videos. This is the first one from 2010. It's a band 3, but this was back when the substitution for sine squared x was not on the reference sheet. So these questions will probably be a bit more challenging in more recent HSC papers, but for now, we'll just pretend it's not. So we have the derivative of a function is sine squared, and we want to find the original function, given that the function evaluated at 0 is equal to 2. All right, so if we want to go from a derivative back to an original function, we want to do differentiation in reverse, which means we need to do some integration. So the function is going to be the integral of sine squared x dx, okay? And sine squared is an integral we've done many times today already. We make our substitution and write sine squared as a half of 1 minus cos 2x. Now we do some calculus. 1 turns into x, just like before. Cos goes to sine, dividing by 2 plus c. Now that right there gets you 1 mark. The other mark in this question is for figuring out what the value of the constant is by using the information in the question. The question says that when we let x equal to 0, the value of the output, or the function, or the y, should be equal to 2. Okay, so there's our function from our integration. We don't know what the c is, but we're going to figure it out. We're going to say if we let x equal 0, the answer should be equal to 2, and we can use that information to solve for c. So when we sub in x equals 0, we can set the left-hand side equal to 2. This one's really nice because we just get 0 minus 0 plus c. So we can very quickly get the other mark by establishing that c is equal to 2. And then we can go back and say, well, that means the function is x over 2 minus sine 2x over 4 plus 2 to get our full marks answer. Which I did. Okay, very cool. All right, if you got the same thing, well done. You're doing really well. Let's finish off with a bit of a tougher one. This runs from 2020, so it's more recent, and it's a band 4. It's 3 marks, but if you just know where to start, like before, and this is very similar to a question we've already done today, this one is really achievable. So let's find the useful information from our reference sheet. Hey, here it is. Cos times sine is equal to a half of sine plus minus sine minus. We've already used this today. This is our second application, and if you're new to do this in 2020, it's a very quick way to get a nice easy 3 marks. Okay, so using our products, we can write our cos times sine as a half of sine 8x by adding them together, and then minus sine of 2x by subtracting them. So rewriting our integral, putting the half out the front, and writing it as the subtraction of sine 8x and sine 2x. And now straight away, the question has just become so much easier. We can go ahead and do some calculus now. So sine integrating to negative cos, dividing by the derivative, which is 8. Sine, or negative sine, integrating to cos, because the two negatives cancel out. Dividing by 2 as always, and now we're just going to sub in our values and simplify as best we can. Okay, so when we sub in a half, 8 times a half is equal to 4, so we get cos of 4 pi here. And then 2 times a half is just pi, so we get cos pi here. We can't just do a 0 on the end because cos 0 is not equal to 0. Cos 0 is equal to 1, so these will actually be values we need to evaluate. So let's make a bit more room. All right, so let's think about cos 4 pi. Cos 4 pi is the same thing as cos 2 pi, which is the end of the cos curve, which is equal to 1. All right, cos 4 pi is equal to 1 because it's the end of the curve. Cos pi is the part in the middle of the curve, which you can see me sort of tracing out with my mouse now. So cos 180 is equal to minus 1. And if you ever forget these values, that's why you have a calculator. You can just type in cos 180, see what it says. Shortcut, done. So evaluating these, we have cos 4 pi equal to 1, so we have negative 1 over 8. Cos pi equal to negative 1, so this plus turns into a minus, and we have 1 over 2. Then over here we have minus 1 over 8, which is just here, and then we have minus plus 1 over 2. So they all turn into fractions. We can simplify them and then just multiply our answer by a half. Everything inside here just turns into negative 1 because a lot of stuff just cancels out, like the negative 8 and the plus 1/8. So we just end up with a half times negative 1, and we get our final answer of negative a half to get 3 marks in the 2020 HSC for a band 4 question. So if you try this by yourself and you got negative a half before I spoiled it, congratulations and well done, and good luck on the rest of your journey. Okay, that should do it for today. Thanks for watching. I hope that helped you integrate some Trig stuff in the future, and subscribe for some more free Extension 1 lessons in the future when I get time. All right, bye for now, not forever.